How's it going, guys? Welcome back to another online video tutorial series. My name is Brock Grant, and today we're going to be going through a bit of stoichiometry. So before starting this topic here, I recommend that you check out the first video of this series, and you also have a look at the composition of compounds and chemical equations, and make sure that you're confident in able to convert your units. That's something that will be a reoccurring theme throughout these videos. So let us look now at the first question. So calculate the number of grams in the following quantities. So I'm looking here, so we've got 0.00844 moles of nickel sulfate. And the question says calculate the number of grams. So I'm just going to put a square bracket there. Now, what I'm looking at here is I see moles, I see a grams, which is mass. So the first equation that pops into my head is moles is equal to mass over molar mass. So I'm going to put in our moles. So it can be 8.44 times 10 to the power of negative 3 is equal to the mass. So the mass we don't know, so we put that as x, over the molar mass. So the molar mass is, so we've got nickel, so we have nickel, we have sulfur, and we have oxygen. So we have 1 nickel, 1 sulfate, and 4 oxygens. So if we add all of those together, that gives us a molar mass of 154.7. So we rearrange this equation, so we grab this, because we see that the operation between the x and the 154.7, that's a divide. So by grabbing this and moving it over here, that's going to turn it into a multiply. So we have 154.7 grams per mole times 8.44 times 10 to the minus 3 mole is equal to the mass. So the mass is equal to 1.31 grams. So that's a nice and simple one. These questions like this don't often come up that much because they are very, very simple, very easy. However, you can expect to do something like this as a part of a bigger question. So that's very important to develop these links to realize, okay, I want to convert moles to mass and then use mass, use the density to convert mass to volume. It's being able to connect the dots. That's where the real difficulty comes in. And if you can do that, that's where you can really score the big marks. So we've now figured out our mass for this one. We're going to look at our next question, which actually involves density. So we have 75 mils of potassium chromate. So we've got density is 1.175 and 20% by mass potassium chromate. Now, here's what's jumping to mind at me so far. I go, okay, I've got my, my volume here. We've got a percentage here when we've got a density. So the overall question is asking for a mass. So which way do I go first? Do I do the 20% first or do I do the density first? The answer is we must do the density first. And this is one of those things where reading the question carefully is very important because we look here and it's 20% by mass. So we have to convert it to mass first, then take 20% of that, then we'll have our answer. So the big giveaway as well is we have our density here. So we go, so the density which is provided, this is 1.175 grams per mil, is equal to the mass, which again, we don't know. That's what we're trying to do here, over the volume. So we have the volume over here. So again, we rearrange this, we grab this 75, we move it over here. And that's going to give us, if we punch that into our calculator, 88.13 grams. So we now have our mass. This is where we take the percentage here, because we know 20% of this raw mass is potassium chromate. So 88.13 grams, and we multiply it by 0.2. Because remembering when we're turning a percentage into a number, we place it like this. So if you do get a little bit confused by that, just think of what is 1/2. So 1/2, 0.5, which is the same as saying 50%. So we now take the percentage here, so we go 88.13, we multiply it by 0.2 or 20%, and that will give us 17.63 grams. And that is our mass. Okay, let us now look at question 10. So something I should have mentioned earlier, make sure you pause the video, have a go yourself, and then we'll work through it together. So the question here states, given the equation, and we have our equation here, how many moles of sodium sulfate, so I'll put a square bracket around that, will react with 21 moles of sodium hydroxide? So we have 21 moles of sodium hydroxide, and we want to know how many sodium sulfate. Now, here's the big thing. Normally, a lot of people would be really tempted, okay, we've got moles, we've got a molar ratio, let's jump straight into it and compare them. So we can see here there's a coefficient of 1, coefficient of 1. So it means it must be 1:1. Therefore, sodium sulfate equals 21 mole. No deal. That is incorrect. Because what we've done is, and again, it's so easy to do this when you're stressed and you're panicking in an exam, is we haven't had a look at our equation properly. Okay, so we need to balance the equation first and make sure that it's balanced on both sides, because remember, we cannot answer any of these questions unless the equation is balanced. So what we do is we draw up our table of all of our elements and we do a count. So we look here, we've got 1 sodium, we have 1, 2, 3 hydrogens, we have 1 sulfur, and we have 4 and 1 is 5 oxygens. Now we look on the right-hand side. So we look here, we can see our oxygens and our sulfurs are balanced, which is great, but our sodiums aren't. So how I'm going to fix that at first is I'm going to place a 2 here. So that's going to get our sodiums nice and balanced. So that means we're going to have 2 sodiums on the left, but that's also going to bump us up to 4 hydrogens and 6 oxygens. Okay, so our sodiums are balanced, our sulfurs are balanced, but if we have a look here, we're 2 hydrogens and 1 oxygen short. So that's easily rectified. We just place a 2 here, meaning that we now have 4 hydrogens on the right, and we have 6 oxygens on the right, meaning that everything is nice and balanced. So now that our equation is balanced, we can now have a look at our molar ratios here. Because, yes, with sodium hydroxide, we have 21 moles, but the ratio between sodium hydroxide and sodium sulfate is 2:1. Because for every 2 molecules of sodium hydroxide, we only make 1 of sodium sulfate. So that means that the molar concentration of sodium sulfate is 21 moles divided by 2. And that gives us 10.5 moles. Okay, so let us now push on to question 14. So again, please pause this video, have a go at it yourself, and then press play and we'll run through it. So, certain metals can displace hydrogen from acids to produce hydrogen gas and a salt. Okay, so this is sort of telling us in words the reaction, what's going on here. So that's helping us to paint a picture of sorts. So when 25.2 grams of aluminium metal are placed into hydrobromic acid, how many grams of aluminium bromide will be produced? So this is a good example of where nomenclature of inorganic compounds is coming into play. So yes, the question isn't directly stating what is the name of this compound, okay? It's not asking you that, but knowledge of that module is essential to understanding this question. because otherwise you wouldn't know what these names mean and what they represent in terms of chemical formula. So, big thing here. Certain metals can displace hydrogen to produce a hydrogen gas and a salt. Okay, so that's giving us a hint. So when we've got 25.2 grams of aluminium metal, so we've got aluminium, are placed into hydrobromic acid. So you need to know that. So that's HBr. Do an arrow. So how many grams of aluminium bromide? So I'm just going to do AlBr will be produced. So we can see here that it will produce a hydrogen gas plus H. Now, this is not correct. This doesn't work. Because again, if we think back to our valence electrons, what is the overall charge of aluminium? So aluminium has 3 electrons in its outermost shell. So it is going to be plus 3. But if we think of bromide, how many electrons does bromide have in its outermost shell? So again, you can look at it on the periodic table. So we can see with aluminium over here, so it has 1, 2, 3. So it has 3 valence electrons. Whereas if we've got bromide down here, bromide has 1, 2, do not count the D shell. Okay, remember, valence is only S and P. So it's 1, 2, 3, 4, 5, 6, 7. So bromide has 7 electrons in its outermost shell. So because it has 7, it wants to steal 1, giving it a charge of -1. Now, how do these, in what combination can these guys combine together to give an overall neutral charge? So we have aluminium, which is +3. The overall charge is going to be neutral. So how many bromides does it need to attach in order to become neutral? And the answer is 3. Because we have -1 times 3 is going to give us -3. So +3 minus 3 equals 0. Now it's the same with hydrogen. Hydrogen cannot exist like this, okay? Because it needs 2 electrons in its outermost shell to be stable, it needs to bind with something else. And hydrogen, like chloride, like iodine and bromide, they are diatomic molecules. So it means that we're going to have H2. Now, before we get too excited, and again, before we push on into doing the raw calculations, we need to look carefully and go, is our equation balanced? Because straight away, I can see we have 3 bromides over here, 1 bromide over here. So what I'm going to do is now, I'm going to have a look, we're going to draw our table up and we're going to start to balance it. So aluminium, we have 1, hydrogen, we have 1, bromide, 1. Nice and easy. On the right-hand side, we have 1 aluminium, we have 2 hydrogens, and we have 3 bromides. So this one gets the same deal because we have an odd number here. Okay, we've got odd ratios. I'm going to multiply everything in the equation by 2. So we're going to have 2 aluminiums, 2 hydrobromic acid, 2 aluminium bromide, and 2 hydrogen gas. Now, the first thing I'm going to do is I want to try and balance up my bromides here. So we can see that we need 4 more bromides. So I'm going to change the coefficient 2. I'm going to change that to a 6. So that's going to give me 6 bromides. And that's also going to give me 6 hydrogens. So our aluminiums are balanced, fantastic. Our bromides are balanced, hydrogens still aren't, but that's easy enough done because we need 2 more hydrogens. So I'm going to change this to a 3. So that means our equation is now nice and balanced. So now that our equation is balanced, we can now push on with our calculations. So we have 25.2 grams of aluminium metal, and we need to calculate the mass of aluminium bromide. So what I do here is we're going to convert our mass into moles. So moles is equal to mass over molar mass. So moles is equal to the mass, which is 25.2 grams, divided by the molar mass. So we have a look at aluminium, and it's 26.98. So we can round that to 27. So our number of moles is equal to 0.933. Now, what we need to do now is we need to take into account the coefficients. Now, there is multiple ways that you can do this. What I personally do, and again, if your way is different, that's a-okay. But I always divide it by the coefficient. So we can see here that our coefficients here are the same. So technically I don't have to. I just find it to be a very good habit. So I will go 0.933 mole divided by 2, and that will give me 0.466 mole. Now that we have calculated our moles of aluminium, we can now move this over to the other side. So we know that the mole of aluminium bromide is equal to 0.466. So we're now going to take this molar concentration and we're going to multiply it by the coefficient up here. So we've got our moles is equal to 0.933. So now we have our moles, we can now convert it into a mass. So we go moles is equal to mass over molar mass. So 0.933 mole is equal to the mass, which we don't know, divided by the molar mass. So again, with our molar mass, we have 26.98 and we have 79.9 times 3 because there are 3 bromides. We have 79.9 times 3 plus 27, and that will give us a molar mass of 266.7 grams per mole. So what we do here is we go 266.7, we move this over to the other side over here, and that will give us 248.8 grams. Okay, so now let us push forward to page 186, question 24. So in the following equation, determine which of the reactants is the limiting reactant. So what I'm going to do is I'm just going to rewrite this chunk over here. So what I'm going to do here, again, when we're comparing two things, especially with the limiting reactant, we need to convert them to moles. We go moles is equal to mass over molar mass. So moles is equal to the mass, which is 50 grams, divided by the molar mass. So you do not include the coefficient here when you're calculating the molar mass. You ignore that, okay? We deal with that when we look at the molar concentration. So we look at the molar mass for beryllium, nitrogen, and oxygen. So we have 209 plus 14 times 3, because remember there's 3 lots of nitrogen, plus 16 times 9, because there are 9 oxygens. So we add all of those together, and that gives us a molar mass of 395 grams per mole. So we go 50 divided by 395, and that will give us a molar concentration of 0.127 mole. And it's now that we take into account this coefficient up here. So we divide this by 2, and that gives us 0.06 mole. Now we do the exact same step, but for hydrogen sulfide over here. So we go moles, mass, molar mass. So we look at the periodic table. So we calculate that. So we go 6 divided by 34. So we punch that into our calculator, and that gives us 0.176 mole. Now we divide this by 3 because there is a coefficient up here of 3, and that gives us a final molar concentration of 0.059, making this one here the limiting reactant. And this is where you have to be very, very careful, okay? A lot of people will not take into account the coefficient at the front here. And because of that, and if we hadn't have taken that into account, we would have gotten the answer quite clearly wrong. So make sure you do take into account those coefficients at the front and make sure you divide by them accordingly to see which one is the limiting reactant.